Welcome to today's paper reading. Today's paper is titled Large Language Models on Graphs, a Comprehensive Survey. This paper, published in the Journal of LaTeX Class Files, is authored by Bowen, Jiang and colleagues from the University of Illinois at Urbana-Champaign and the University of Notre Dame. The abstract highlights the significant advancements made by large language models, LLMs, like GPT4 and LLaMA in natural language processing. These models excel in text encoding and decoding and have shown emergent reasoning abilities. However, many real-world scenarios involve text data associated with structured information in the form of graphs. The paper categorizes these scenarios into pure graphs, text-attributed graphs, and text-paired graphs. It also discusses various techniques for utilizing LLMs on graphs, such as using LLMs as predictors, encoders, and aligners, and compares the strengths and weaknesses of different approaches. Additionally, the paper covers real-world applications of these methods and provides open-source codes and benchmark datasets. The abstract concludes by pointing out potential future research directions in this rapidly evolving field. Large language models, LLMs, have shown significant capabilities in various natural language processing, NLP, tasks such as question answering, text generation, and document understanding. These models come in different architectures, including encoder-only, decoder-only, and encoder-decoder structures, with no fixed size thresholds. As LLMs are increasingly applied to text data associated with structured information in the form of graphs, new challenges arise in how to effectively encode this graph structure. This integration opens up potential for LLMs to address fundamental graph reasoning tasks. The techniques for applying LLMs to graphs can be categorized into LLM as predictor, encoder, and aligner. Despite the growing interest, there are limited surveys that explore this intersection comprehensively. Our paper aims to provide a thorough review of LLMs on graphs, making it accessible to a broader audience. Figure 1 categorizes the scenarios where large language models, LLMs, can be applied to graphs based on the relationship between graph and text. The scenarios are divided into pure graphs, text-attributed graphs, and text-paired graphs. Additionally, it summarizes 3 techniques for utilizing LLMs on graphs: LLM as predictor, LLM as aligner, and LLM as encoder. In the LLM as predictor technique, LLMs are responsible for predicting the final answer. The LLM as aligner technique involves aligning the inputs-output pairs with those of graph neural networks, GNNs. Lastly, the LLM as encoder technique uses LLMs to encode and obtain feature vectors. These techniques and scenarios are crucial for understanding how LLMs can be integrated with graph data to enhance various applications. In this section, we define various types of graphs and introduce the notations used in the paper. A graph is defined as G equals VE, where V is the set of nodes and E is the set of edges. We also discuss graphs with node-level textual information, denoted as G equals VED, and graphs with edge-level textual information, also denoted as G equals VED. Moving on to language models, we highlight the evolution from BERT, which uses masked language modeling, to more recent models like Roberta and Electra. Finally, we introduce graph neural networks, GNNs, including models like GCN and GraphSage, and graph transformers, which use attention mechanisms for node and graph-level tasks. Figure 2 presents a comprehensive taxonomy of how large language models, LLMs, are applied in various graph scenarios and the techniques used to integrate them. The taxonomy categorizes the applications into different graph scenarios such as pure graphs without textual information, text-attributed graphs, and text-paired graphs. It also outlines the techniques employed, including heuristic reasoning, algorithmic reasoning, and rule-based approaches. Each category is accompanied by representative examples, showcasing the diverse ways LLMs can be leveraged to enhance graph-related tasks and analyses. In this section, the authors introduce a categorization of graph scenarios where language models can be adopted. They classify these scenarios into 3 types: pure graphs, text-attributed graphs, and text-paired graphs. Pure graphs are those without textual information, such as traffic graphs. Text-attributed graphs include nodes or edges with rich text information, like academic networks. Text-paired graphs have textual descriptions for the entire graph structure, such as molecules with captions. Additionally, the authors categorize techniques for using large language models, LLMs, on graphs into three main types: LLM as predictor, LLM as encoder, and LLM as aligner. The framework for training and inference with language models on graphs is also summarized. In the following sections, detailed methodologies for each graph scenario will be discussed. Pure graphs serve as a universal representation format in graph theory, crucial for understanding and solving a wide range of algorithmic problems in computer science. These graphs are essential for providing theoretical solutions and insights for real-world applications. Language models, particularly large language models, LLMs, have shown significant potential in graph reasoning tasks due to their emergent reasoning abilities, which are partly attributed to their autoregressive mechanism. However, integrating LLMs into graph reasoning presents challenges, including the need for computation capacity beyond traditional graph neural networks, GNNs, and the inherent limitations of handling complex, indefinite complexity tasks. Text-attributed graphs are prevalent in various real-world scenarios such as academic and legal networks. These graphs necessitate the encoding of both textual information associated with nodes/edges and structural information within the graph. The role of large language models, LLMs, in these graphs can be categorized into three types, as predictors, encoders, and aligners. Predictor methods use LLMs as the main model architecture to capture both text and graph structure information. Encoder methods extract textual features to serve as initial node feature vectors for graph neural networks, GNNs. Aligner methods involve an LLM component for text encoding and a GNN component for structure encoding, which interact to mutually enhance each other. All surveyed methods are summarized in Appendix Table 6, with detailed descriptions provided in the following sections. Figure 3 provides a visual illustration of the different methods used to integrate graph structure information into language models, LLMs. The figure categorizes these methods into three main types: A. Rule-based graph as sequence, where graphs are linearized into text sequences using predefined rules. B. GNN-based graph as sequence, which employs graph neural networks, GNNs, to encode graph structures into special token representations. And C. Graph-empowered LLMs, where the architecture of the LLM is modified to jointly encode both text and graph structures. Each method is depicted to show how graph information is processed and integrated into the LLM, highlighting the distinct approaches and their specific applications in enhancing the model's ability to understand and utilize graph data. Figure 4 illustrates various techniques related to using large language models, LLMs, as encoders. These techniques include A. One-step training, where the LLM and graph neural network, GNN, are trained together in a cascaded architecture for downstream tasks. B. Two-step training, which involves first adapting the LLM to the graph and then fine-tuning the entire LLM-GNN pipeline. C. Data augmentation, where LLMs are used to generate additional text data for the LLM-GNN cascaded architecture, enhancing its performance. Each of these methods aims to leverage the strengths of both LLMs and GNNs to improve the representation and understanding of textual and structural information in graph-based tasks. Figure 5 illustrates the methods where LLMs act as aligners, focusing on two main categories: LLM-GNN prediction alignment and LLM-GNN latent space alignment. In LLM-GNN prediction alignment, the LLM and GNN are trained iteratively with the LLM generating labels from text and the GNN from structure, which serve as pseudolabels for each other's training. This mutual enhancement results in a joint text and graph encoding. LLM-GNN latent space alignment involves connecting text encoding, LLM, and structure encoding, GNN, through cross-modality contrastive learning, aiming to align the latent spaces of both modalities. This approach is exemplified by methods like Congrat and Grenade, which use graph-specific elements and neighbor-level knowledge alignment, respectively. These methods highlight the potential of LLMs to integrate textual and structural information in graph-based tasks. The application of large language models, LLMs, on graph-captioned graphs, particularly molecular graphs, involves integrating text information with graph structures. This integration can be approached in several ways, using LLMs as predictors, designing graph-empowered LLMs, and aligning latent spaces. For molecular graphs, common methods include using SMILES and NCHI for linearization, as well as more advanced methods like selfies and deep smiles. Different LLM architectures are employed based on the task, such as encoder-only models for understanding, encoder-decoder models for generation tasks, and decoder-only models for advanced generation capabilities. Figure 6 illustrates the methods used by large language models, LLMs, for text-paired graphs. The figure outlines three main approaches: A. Rule-based linearization, which involves converting graph data into a sequence format that can be processed by LLMs. B. Graph-empowered LLMs, where the model architecture is designed to encode both text and graph structures. And C. Latent space alignment, which aligns the latent spaces of graph neural networks, GNNs, and LLMs through contrastive learning. These methods aim to enhance the ability of LLMs to understand and predict properties of molecules and other entities represented in text-paired graphs. In the context of pure graphs, common problems include connectivity, shortest path, and graph diameter. GraphQA benchmarks these problems in real-world scenarios. Accuracy is the primary evaluation metric. For text-attributed graphs, tasks such as node classification, link prediction, and edge classification are prevalent. Evaluation metrics include accuracy, macro F1, and micro F1. Text-paired graphs involve various data splitting methods and tasks like graph classification and regression. BLEU score is used for text generation evaluation, while heuristic methods evaluate molecule generation. Table 2 provides a comprehensive summary of datasets used for evaluating models on text-attributed graphs. These datasets span various domains such as academic, e-commerce, book, social media, and Wikipedia. The primary tasks evaluated on these datasets include node classification, link prediction, edge classification, regression, and recommendation. The evaluation metrics vary depending on the task, with common metrics including accuracy, macro F1, micro F1 for classification tasks, and mean reciprocal rank, MRR, normalized discounted cumulative gain, NECG, hit ratio, HIT, for link prediction and recommendation tasks. For regression tasks, mean absolute error, MAE, and root mean square error, RMSE, are typically used. Table 3 provides a comprehensive overview of text caption graph datasets, detailing the tasks they support and their respective sizes. The tasks include pre-training, PT, fine-tuning, FT, captioning, CAP, graph classification, GC, retrieval, RETR, and graph generation, GEN. Each dataset size is annotated with the number of graph text pairs, graphs, and assays. Additionally, the Source and Notes section offers insights into the origins and specific characteristics of each dataset, aiding in understanding their utility and potential applications in graph-based machine learning tasks. The authors identified the need for better benchmark datasets to evaluate LLMs on various types of graphs, including homogeneous, heterogeneous, and spatial temporal graphs. They also suggest exploring a broader task space for LLMs, such as applying them to text-attributed and text-captioned molecular graphs, and using them for data augmentation. Additionally, they highlight the challenge of making LLMs more efficient on graphs, particularly in terms of graph linearization and model optimization, and propose the development of graph-aware tuning methods. Another direction is to improve the generalizability and robustness of LLMs on graphs, ensuring they can transfer knowledge across domains and maintain consistent predictions under obfuscations and attacks. The authors also explore the idea of multimodal foundation models, questioning whether a single model can unify different modalities like texts, graphs, and images, or if domain-specific architectures are necessary. Lastly, they propose the concept of LLMs as dynamic agents on graphs, suggesting that simulating dynamic knowledge retrieval through multi-hop reasoning could help correct LLM outputs and reduce hallucinations. In this paper, the authors have provided a comprehensive review of large language models on graphs. They categorize graph scenarios where LLMs can be adopted and summarize the large language models on graph techniques. A thorough review, analysis, and comparison of methods within each scenario were conducted. Additionally, the authors summarized available datasets, open-source codebases, and multiple applications. Finally, they suggested future directions for large language models on graphs, emphasizing the importance of advancing this field and its potential impact on various domains. This research has been supported by several key funding sources. The primary contributors include the U.S. DARPA INCAS program, the National Science Foundation, and the Molecule Maker Lab Institute. Additional support has been provided by the Institute for Geospatial Understanding, the U.S. DARPA IDM program, and the USDA National Institute of Food and Agriculture. The National Science Foundation has also awarded several grants to support this work, including awards number 214-2827, 214-6761, and 223-4058. It is important to note that the opinions and conclusions expressed in this research are those of the authors and do not necessarily reflect the views of the funding agencies. Thank you for watching.